Well, good evening, ladies and gentlemen. Welcome to Rhodes House on this rather lovely English summer day. My name's Ian Wormsley. I'm the director of the Networked Quantum Information Technologies Hub, which is a consortium of 9 academic partners led from Oxford, which has the ambition to build the first components, the first engine for a quantum computer. Now, in case you don't know what that is, my colleague, Professor Winnie Hensinger, is going to give you that introduction here. His title is The World's Most Incredible Machines, and he's absolutely right. They're the kind of machines that you can only understand when you have one. And that's really, really astounding. Now, you know, I've come across machines like that before, too, but it turns out somebody understood them. Anyway. So it's a great pleasure to have Winnie able to give this public lecture. He's a professor of quantum technologies at the University of Sussex and a member of the NKIT consortium. He obtained his undergraduate degree at Largescale Universiteit in Heidelberg and moved to Queensland, the University of Queensland in Brisbane, to complete his master's degree. He also did a PhD there, demonstrating novel quantum effects with neutral atoms, working with 2 leaders in the field, Helena Rubinstein-Dunlop and Gerard Milburn. He spent some time at NIST in Gaithersburg in the US in the group of Bill Phillips following his PhD, where he was interested in a phenomenon called dynamical tunneling, which is a sort of wacky quantum effect where atoms move in unexpected directions when you tickle them. He's not going to talk about that today. Well, you're talking about tickling atoms, but in a different way. He then spent some time at the University of Michigan, where he first got interested in ion traps and their applications in quantum information processing. And he took that interest with him when he started at Sussex in 2005. He now leads the Ion Technology Group there and is the director of the Sussex Center for Quantum Technologies. So he's been working on ion trap microchips and has developed some new ways to think about using those in building a new generation of quantum computers. And no doubt he will say something about that today. So his work within NKIT and separate from that is one of the ways in which we're really pushing in the UK the boundaries of this emerging field of quantum technologies. And I hope that you get from his lecture, I'm sure you will, some of the sense of excitement for the things that we believe can be accomplished in the next few years by harnessing this really intriguing and counterintuitive theories around quantum physics. So, over to you, Winnie, and I will move off the stage so that your motions don't knock me off. Good. Welcome.
Thank you, Ian. Thank you for the very kind introduction. And yeah, I'm moving all over the place, so it's a good thing to step aside. So, also got a stick. I can't use a laser pointer, so in good Oxford tradition, I'm using a stick to point to things. So let me start by saying I very much like you to ask questions, and I very much like you to ask questions during my talk. So I don't care about completing my slides. So please absolutely feel free to ask me anything you'd like. Right. So Ian already gave some ideas of the background of quantum computing in the UK. So there's what's called a UK Quantum Technology Hub, and this hub is in tasked with developing quantum computers in the UK. This is a consortium of multiple universities, and they do a lot of fantastic things. I'm going to zoom in my lecture on 2 things today, and on actually building quantum computers. And in fact, there will be 2 demonstrator quantum computers, and you'll hear about this in my talk. A machine to be constructed at Oxford, the 2020 engine, and a machine at Sussex. And you'll hear all about what we're going to do to make this happen. So most importantly, let me actually start by saying who are the people who are doing all this work. So it's unbelievably complicated, as you'll find out in my talk, trying to build a quantum computer. And this would not happen unless I would have an outstanding team of people. And you can see a picture of them here. And we are growing teams. So if you're interested to become a quantum computing researcher, think about it. And obviously, very importantly, I should also acknowledge the funding agencies, both here in the UK, in Europe, and abroad, and companies who allow us to make this happen. So let me start my talk with an invitation. So on Tuesday in London, we're actually going to make a walk-in quantum computer. So in the middle of London at Spitalfields Market. If you're interested, come and feel, touch, and experience a quantum computer, a very authentic installation. It's not a real thing. We can't yet move a real thing. So please feel free to come. It's all day on Tuesday in the middle of London, Spitalfields Markets. Right. So quantum physics is unbelievably weird. So this is a very good description of quantum physics. A mechanical object, a thing, can be at two different places at the same time. So I can be here and I can be standing over there at the same time. It actually works in quantum physics. That exists, and that's what we refer to as superposition. So an atom can move forward and backward simultaneously. So imagine you're sitting in your car, and imagine you're going to get out of this parking space, and rather than just hitting the car in front of you, you also hit the car behind you. That's quantum physics for you right there. This is, in fact, what I achieved in my PhD, and it didn't even destroy any cars. So an object can tunnel through a solid wall. And then there's what Einstein called spooky, what freaked out Einstein. He's a very smart man. Entanglement, and we'll get to talk about this in the lecture. So these are very strange things. So quantum physics is very counterintuitive. It's unbelievably weird. It's nothing you experience in your daily life. And this is about quantum computing. So let's start talk about computing. And this is the first transistor. And right now, half of you have an iPhone or a fantastic computer, but that is your first iPhone right there. And I'm going to show you this because, as you're going to find out in my talk, we're kind of here with developing quantum computers. Now, Richard Feynman was an unbelievably imaginative physicist, and one of the things he asked is what happens when we make these transistors I showed you very, very small, so small that they're on a single atomic scale. And what he thought is actually, look, things are going to behave very, very strange, and rather than just making this a problem, he thought it's about an opportunity. And he was the one who actually first proposed the idea of actually building a quantum computer when things behave according to these very, very strange effects I've just told you about. Moore's law. So if you buy a computer, how many hands up who's bought a computer in the last year? Great. So how long did it take you to replace your old machine? And so when did you buy the one beforehand? Hands up, who took it 3 years to buy a new one? 3 years? 4 years? Okay, 5 years? Come on. Okay, so 1 year? Okay, so basically what Moore's law is saying that computers double the classical conventional computers double their speed every 1.5 years or something like that. And that seems like an impressive thing. But at the end of the day, that's not so impressive if there are certain problems which would take even the fastest computer right now billions of years to calculate. But more importantly, Moore's law is actually coming to an end. So this is a newspaper article saying that Intel thinks we're in trouble. We can't, when we make things smaller and smaller, we can now get to single atoms, and now we can't increase the computational powers of processors any further. So what is quantum computing? So quantum computing is a new type of technology. It's an entirely new thing. It's not an iteration of classical computing. It's not a fast conventional computer. It's an entirely different technology. So even using the word computer is a little bit misleading because it makes you think it's a new model. It's like a faster model. It has slightly different things inside, but it's really a different thing. And the key thing you need to know about quantum computing, it will probably evolve along a very similar trajectory as conventional computers. So that means we are right now in the 1940s of conventional computing in terms of building quantum computers or doing the programming. It's nothing, you can't just use a classical computer program, you can't just use a JavaScript, run it on a quantum computer and it runs really fast. So you're not increasing the clock speed, it's a whole different and a whole new technology. So this is the key question you're going to ask, what can actually a quantum computer do? So we really want to do now that. And so this is the answer, and if you walk out of this lecture, if you know, that's all you know, then this is already quite good. So you can solve certain problems which would take the fastest supercomputers or a secret NSA machine you don't know anything about somewhere in the desert. Even that machine would take 1 billion years to compute what a quantum computer could do maybe in a few minutes or a week. So it's entirely problems which you thought you could never ever solve on any computer which a quantum computer can solve. But not all of the problems, some problems. And for the mathematically minded people in the audience, it changes the actual scaling of how a problem is being solved. So imagine if I want to if I want to factorize a number, say 9, I can do this in my head, right? I can say, okay, that's 3 times 3. Now, if I give you a very large number, nobody in this room will be able to do this. And even a really fast conventional computer can't do this because the scaling means like how big is the problem, how long is the number. And quantum computers change that scaling, and so that's what makes quantum computers really different. So it goes from, say, exponential to polynomial or things like that. If you want to know what people already found what quantum computers can do, there's a fantastic website. It's called the Quantum Algorithm Zoo. And problems you find there are search. So if you have a large data set and you want to find something, imagine you're going out on a Friday night and you write down a number, but you can't remember that name anymore. If you needed to go through the phone book and look for all the entries in order to find the name corresponding to a number, that's a search problem. Factorization is one of the problems. So in fact, encryption, so RSA encoding, that's the way how you put your credit card details on the internet. That is safe because conventional computers really struggle to factorize large numbers. And a quantum computer would destroy this security in a way, and that's one of the applications of a quantum computer. But there's hundreds, in fact, of algorithms, and this is a very active field of research. What excites me the most personally is something entirely different. Now let me come back to what is quantum physics. Quantum physics is a theory which describes everything around us. So quantum physics describes basically the color of this plastic, the strength of this wood. Everything here in this room is described by quantum physics. And so quantum physics is the underlying theory of nature, of small things, of everything. Now, conventional computers really struggle to exactly calculate quantum physics problems, and as such, we really struggle to understand what's going on inside things. Now, quantum computer, because it uses the very mechanics or the very dynamics of this theory to compute things, it allows us to maybe understand our physical systems in an entirely new way, and that's what's called digital quantum simulation. So this is really, really an unbelievably powerful thing for a quantum computer because it allows you to actually tackle, you can think about understanding conductivity in materials, making room temperature superconductors, making materials lighter but stronger, understanding processes in biology, thinking about protein folding, maybe even creating new pharmaceuticals. All these kind of things rely fundamentally on the very baseline on quantum physics. And so quantum computers may just be an instrument to solve or tackle some of these problems. Right, so we are very smart people. We're in Oxford, Oxford is a fantastic place, and I'm a professor of quantum technologies, so shouldn't I be able to just tell you everything, give you a fantastic good prediction of what quantum computers can do? We are really so far away in technology evolution. Come on, do we really know everything? And so in order to tell you how actually a little naive we are, or how very naive we are, all of us are, maybe not my Oxford colleagues, but certainly most of us are going to want to take you back into history. So chairman of IBM said there's a world market for 5 computers. And that man was successful enough to start a huge company which dominated the whole global computing market. Yet, that was his prediction. Here you go. Very smart man. Not sure whether he had an Oxford degree, but I suspect very strongly, very smart man. Okay, let's look at what people thought when computers were built first. Conventional computers were built first. The electronics people said there were too many vacuum tubes and it would never run. Mathematics people said there were no problems complex enough that computers were needed. Here you go. These are the smartest people at the time, yet had no clue. This is something we need to learn, that at any time in time, we are very naive about new emerging technologies, and we actually know fundamentally very little of where these technologies go. So let's make a comparison here. 1940s, there were around 5 computers and around 50 programmers in the world developing conventional computers. 2017, around 5, maybe 10 computers and barely 50 quantum computing programmers around in the world. Recognize something? This is where we are right now. This is where we are. We are literally right now in the 1940s, not even the 1950s, unfortunately only in the 1940s. So this is what I'm telling you is, be very careful of what people say can or cannot be done with quantum computers, because we are right now at the beginning. There's literally just 50 people doing the algorithms. So let's go and actually have a look how these machines work. So what is a quantum mechanical state? So a quantum physics degree 101 here in just 30 seconds. What is a quantum state? A quantum state represents some kind of property. Like, let's take me. My quantum state could be either standing here on the left, or my quantum state could be standing on the right. And that funny notation here, these little funny brackets up there, that is literally just saying it's the notion for a quantum state. So the atom, I could also do this for an atom. The atom can be on the left, or the atom can be on the right. So that's a quantum state, and now you've learned what quantum states are. So I need now volunteers. Who is happy to volunteer? And any volunteers? Fantastic. So hold on, let me get out some money. I won't pay you, I promise. Right, so I need 2 volunteers, maybe on each side. So you volunteer? Can I have a what's your name? Igor. Igor, fantastic. Igor. Okay, so a volunteer on this side here. Anybody is daring enough to participate in a mad physics experiment? What's your name?
Rohit.
Rohi? Okay, fantastic. So I'm going to try to explain entanglement now. So Rohi, would you please throw this coin a few times and give me the result?
Tails. Okay, tails.
Mm-hmm.
Heads. Heads.
Okay, let's stop here. Okay, so thank you, Roy. Igor, you do the same thing.
Heads. Tails. Falling down, I see a head. Head.
Good. Okay, now I'm going to tell you what is actually entanglement. So these 2 gentlemen here have participated in a lovely physics experiment. Now imagine, these are non-fake coins. I took them out of my wallet, so there was no foolery. But imagine you would have got the same sequence as Igor got, right? Imagine you both got the same sequence of heads and tails, right? But I didn't fool with these coins. I didn't manipulate. And basically, you can do any experiment in the world you want to do, and you always find a random sequence of head and tails, and you can do the same thing. You do a sequence of throws, and you always get heads and tails, but strangely enough, when we then compare the results, they're always the same. And that is entanglement. And even if you guys never speak, I kind of cut your phone lines off, I put you on the other end of the universe, you're still going to get the same result. But in any experiment possible, you cannot find anything wrong with this coin. It's a fair coin, yet you always get the same results. That's one way to think of entanglement. Entanglement is one of the, thank you very much, guys. Excellent. Thank you. Oh, you can keep it. Oh, thank you. Great. This is only 10p. That's all but my salary gives out. Thank you. Thank you, guys. All right. So that is now you understand entanglement, and that's one of the key things which you need inside a quantum computer. So now let's start. How do we actually build a machine? What I need, anybody has heard, hands up who knows about bits? Bits? Good, okay, oh, fantastic, you guys are great. So bits is basically like a language just like letters, and it's sequences of zeros and ones, and these zeros and ones provide information. And your classical computer, your iPhone, basically just uses a sequence of zeros and ones in order to represent information. Quantum computer does the same thing, only now we've got this quantum bit, and now he goes really mad, because quantum bits can be 0 and 1 at the same time. Okay, now that doesn't really sound like that unbelievable or that crazy, but let's have a closer look what happens if we're gonna have 2 bits. So I'm gonna now have a memory stick, a classical memory stick, but it's a very old one. So my memory stick has only 2 bits, right? So I'm gonna write into my 2 bits, say for example 0, 1. That is one particular combination. Now, if I have 2 quantum bits, and here it becomes now the really mad thing, I can write in 0, 0, 0, 1, 1, 0, and 1, 1, all at the same time. So classical 2 bits, I have 1 number, 2 quantum bits, I get 4 numbers. Now, okay, you're gonna say, that's okay, but that's not really that great. Now let's see what happens if we have 100 bits. Now again, I need some help here. Who can say this number? Anybody can say that number? From Oxford? Is it an Oxford degree? Oh, okay, so I can't, to be honest, I don't think there's even a name for I don't know how to say that number. But anyway, so that's a very large number. That's the number of different combinations, the number of different information, number of different numbers you can encode into just 100 quantum bits. That tells you something how powerful a quantum computer actually is. And this, in a way, gives you a feeling of why quantum computers are so unbelievably powerful, because you can do all these combinations simultaneously in 100 bits, whereas in a classical computer you have only one 100-bit number, and here you've got all these different numbers. Right, and so now 15, 20 years ago people started, okay, can we actually build a quantum computer? And scientists across all different fields went away and said, okay, my system is perfect to build a quantum computer. And scientists love that because they're giving applications to something they like to investigate anyway is always a great thing. So literally, scientists all across the world use their favorite physical platform trying to build a quantum computer. And for the last 10 years, it's still kind of going on, but 2 kind of platforms crystallized at the end of the day. 2 platforms which produced really, really good results. Good results in the way that the errors of the computations were very small, and I'm gonna get in a second how small they actually became. So superconducting qubits, superconducting circuits is one of these, and the other platform is individual charged atoms, and we call them ions. So charged atoms, ions, the same thing. Anybody can tell me like how I'm gonna charge something really easily, quickly right now, without any technical help? Anybody can show me how to charge something? Exactly, if you rub your hands exactly right, you take electrons away from your hands. So if you have still hair, unlike me, then you can actually rub your hair, and that will charge them up. So that's kind of what we do with atoms, and we make them into ions. So the kind of bad thing about these superconducting circuits is you actually have to cool them to minus 273 degrees Celsius. And that makes it really hard. It makes it easy, or relatively easy, when you do things with 10 or 20 qubits. But there's bad news. And the bad news is actually, if you want to solve some of the really interesting problems, you're going to need millions or billions of qubits. And so while superconducting qubits are great for small numbers, they're going to be very hard for large numbers. And this is why I, in my personal career, decided very early, this is not what I think is the future. And so I went into trying to build a quantum computer using trapped ions. And so what I'm going to tell you about now is about how you build a quantum computer using trapped ions. And here they are. So each bright dot is one trapped ion. Each bright dot is one quantum bit. And so this is what you see here, one quantum bit at a time, one next to each other. Okay, so let's pick our favorite physics book. So I'm sure here at Oxford you use good old Tom Clancy. So Tom Clancy usually probably is not a physics book, but actually Tom Clancy got it fantastically right when he went to talk about trapped ions. So let's follow Tom Clancy here. You confine ions in webs of magnetic and electric fields, hit a trapped particle with a burst of laser light to send it into an excited energy state, then hit it again to ground it. That's your switch. Rows of ions in a quantum logical gate giving you the smallest, fastest computer on Earth. Neat, clean, perfect. Now I'm going to have to tell you, Clancy lied in the last sentence. As you'll see in a second, it's not clean and neat and clean, but the rest is actually remarkably accurate. So Tom Clancy actually succeeded unbelievably well to explain trapped ion quantum computing in just 4 lines. So let me try to get a little bit in more detail here. So how do you actually trap an ion? So you need a minimum in an electric field, and that's unfortunately not possible. So there's a physics law which completely prevents this. Can't do that, so this is illegal. So it doesn't happen, physics stops us from doing so. There's a little trick. Now have a look at that. So this is a kind of spinning potential here, and if I were to place something in here, it stays trapped. Hands up, who believes that is actually true? Hands up, who thinks I can trap something in there? Hands up, who is critical here? Who is critical? Who thinks you couldn't trap anything in that thing? No, I saw 2 hands. Okay. So I'm an experimental physicist. So obviously, I could give you the equations, but that would be boring. So here's the experiment. So see, if I put a ball on it and it just rolls off, if it doesn't rotate. Now I'm going to let it rotate, and let's see. Here you go. It stays trapped. A spinning potential like that, a spinning mechanical potential, can actually hold something. Right, but now some of you could say, okay, that's all fine, but ions are electric things, are electric particles. What about a spinning electric potential? Now what I'm going to show you next, do not do at home because you will die. So I'm applying a very large voltage between these 2 electrodes. Again, if you were to touch them, that would be very unhealthy. And see in here, magically, these things are just floating, right here. See these particles? They float. The way you make these particles, you rub them, so that charges them up, and you put them in the center, and it means they can now float. So this is a picture that, yes, you can actually trap something using spinning electric fields. So how you make ion traps is by making geometries of electrodes like this, and these electrodes are here in a plane, and the ions are literally just located just above this plane, and they float because of these spinning electric fields and because of the static potentials. You can then even move ions around across the surface. So the ions are floating above an ion trap. We call this an ion trap, these electrodes here. And now you can obviously take this a bit further, and this is a picture, a microchip we developed at the University of Sussex. And so you can see here, it's right here in the center, there's this microchip here. If you zoom in, you see this X junction, and so you can hold ions above these electrodes. And now as you move them along, as you change the voltages on these little squares here, you can now move the ion across, take it around the corner, and you have full control over individual atoms. So it's like a little game of Pac-Man. So you have full control over these atoms, you can transport them, and you can now use a geometry like this, a microchip like this, you can use that to make an architecture for a quantum computer. This is how it looks. This is a vacuum system. Inside this vacuum is absolutely nothing in there. We have to take all the atoms out. In fact, the vacuum inside there is better than out of space. So if you ever have any suicidal thoughts, stepping out of a space shuttle is a lot more healthy in outer space than if you were to find yourself inside this vacuum system. Because there's absolutely nothing there. We pump it completely free of anything, and so then we can hold individual atoms there, and no other atoms interfere with our atoms because they're going to form now our quantum bits. So this is actually a very small quantum computer. So this is right here, you can see. Yes, you have a question?
You said ask a question.
So that's a fantastic question. So I'll just repeat the question for everybody. So isn't that particle a wave? Because in quantum physics, particles are waves, right? And so where the hell is this particle? Where is it? Is it just somewhere here? But the funny thing is, and this is what makes it hard to build a quantum computer, we can actually control atoms in such a way that sometimes they behave as waves and sometimes they behave as particles. For this particular experiment, we make actually atoms behave as particles, and you can think of them as little balls. When they become quantum is when we do these quantum gates I'm going to show you in a second. But for this purpose, you can think of them literally just as balls. This is actually a very accurate representation. Right, here it looks like a lot of mad stuff, a lot of optics, vacuum systems, lasers, electronics, everything. That kind of makes a quantum computer. And now let's zoom in and have a little bit of a closer look. So what has been achieved so far in building quantum computers? And trapped ions have, without a break, always led the field. And so these are some results from groups around the world in making amazing things. So people have entangled already 14 ions, so making these strange correlations I showed before. They even teleported. So this is what got me into the field as a kid. I always wanted to be science officer on the Enterprise, and so here we go, now we've done it. We've teleported things, only atoms. Here at Oxford, David Lucas, who sits over there, managed to get a world record of making quantum gates with unbelievably small errors. Now, people entangled photons and ions, so a lot of fantastic things have been done with trapped ions and really accelerated trapped ions to be a system where we can now say it is realistic and feasible to think of building a quantum computer. So what is actually missing? Why can't we just break all the codes yet and break all the RSA encodings? So it's kind of a little bit like the same as classical computers where we started with vacuum tubes and we kind of have to go to some kind of ENIAC machine like this. And so we need some architecture where you have some kind of memory, just like in your conventional computer, a hard drive or like a RAM. You need some kind of processor where you do now quantum gates instead of classical gates. The classical normal computer has classical gates, here we need quantum gates. And we need one way to bring atoms from one place to another or transport that information. And one of the ways to transport that information is literally to move these atoms using electric fields from the memory region to the entanglement region. And so Ike Chung is a theorist that, actually an experimentalist as well at MIT. He made a little picture, a little movie showing how you were to make a quantum algorithm. So each of these little balls are ions, and you can see here that now these ions are being transported all around, and you see these little light flashes, these are laser beams, and so this is the operation of a quantum computer. And you can see this is just like a game of Pac-Man. So you all have kind of developed quantum computers already, or some of you, the older people probably, some of you haven't even played Pac-Man, but here you go. So how do you now encode a quantum state? How do you encode information into a quantum bit? And so first of all, let's start, what is an atom? An atom is a nucleus and an electron which circles around the nucleus. And in the simplest picture, you encode the state, so the information into the atom by picking different trajectories of the electron around the nucleus. So we call it a spin. People say often the spin, but it's really just the trajectory of the electron. So you can see that here. So one state is going to call 0 from now on. If the electron goes like this around the nucleus, we're going to call 1 if it goes like this. Yes? Absolutely. So you can actually, so an atom is actually a lot more complicated. Atoms tend to be unbelievably complicated with lots and lots of states. So this is just to show there's lots more states. But in fact, sometimes it's hard to even rule out these other states. A lot of the work we do, in fact, is to rule out the additional states. So this is just, in fact, I should have made more circles here, but yeah, we only pick 2 of these. So this little diagram is what we use to illustrate what a gate is. So what that means is we have got 2 bits here, 2 quantum bits, and depending on the state of one of them, we do something to the other. So if the first bit is 0, we do nothing to the second bit. So the second bit stays 0. But if the first bit is 1, then we're going to switch the second one So we're going to switch the second one from 0 to 1. So this is what we call a controlled not quantum gate. So you can see, depending on the state of 1, we do something to the other. That is what's happening here. And now we need to somehow complete the gate. How do we complete the gate? What we actually do is we make use of the fact that atoms, ions repulse each other. Remember, they're charged. If I rub my hair, I mean, not my hair, which is non-existent, but somebody with longer hair, if they rub them, they're going to spread all the way, and that's because of the charge. And so ions do the same thing, so they repel each other. So if I bump one, then the other will move as well. That's what you see here. And we make use of this motion of ions in order to actually mediate to implement a quantum gate, to do something to the second ion conditional on the spin or the electron trajectory of the first ion. So we make use of the motion. And so this is traditionally being done. So all the leading experiments have been done using laser beams. And in fact, the world record of all possible people to build quantum computers has been done using 2 laser beams, putting these laser beams, you wouldn't believe it, laser beams actually can give a kick. So light actually carries momentum, and using laser beams, you can give kicks, and that can then implement this quantum gate between 2 ions. And using this technique, people have now achieved the world record. An unbelievably small error in making such quantum gates. And in fact, again, David Lucas, who sits here, has been holding this world record, probably still holds the world record, making quantum gates like this. And so this is what has given rise to, given rise to the 2020 engine. But I want to tell you something. Why is it so important to look at the error of quantum gates? And that is this principle of fault-tolerant quantum computing. I promise this is the hardest physics concept you're going to hear in this talk, so this is going to be a bit complicated. Basically what it means is, like, in any computer, in a conventional computer, there's errors. But if you have more and more computation, then the error is going to add up, and eventually a computation is always going to be wrong. In a quantum computer, that's the same thing. But what you can show is what very clever theorists have shown, that when you use a certain concept, and that's called fault-tolerant quantum computing and error correction, you can actually, by means of adding additional ions in the process, you can actually compensate all the errors, and you can show that you can complete any computation. And that's the concept of fault tolerance. So this kind of shows you that it's important to have small errors in your quantum gates. And so just to give you a feeling, so what we need to reach in quantum computing is an error of 1% or better. That is very important. And since laser gates have been holding the world record across the aisle in every way, this is obviously a fantastic way to build a quantum computer using such laser beams. And this is a node here which is being constructed at Oxford to build such a quantum computer. You can see this is a vacuum system, very similar to the ones I've shown you before, and you have laser beams going in here, and that then allows you to, on this chip here, so again there's a microchip here, allows you to carry out entanglement gates and so on. Right, so what do you do when you go bigger? And this is a real challenge. So what are you going to do when you go from 20 ions to 200, to 2,000, 2 million, 2 billion ions? And so this is, in a way, what makes it very hard, because, like, I've got a laser pointer here, which I'm not allowed to use on the screen, but imagine I'm going to have 2 billion laser pointers and all have to align them in a fantastic way. That's very hard and a lot of engineering involved. And so this is what motivated my group at Sussex to trying to think of a different approach which does not use laser beams to make these quantum gates. And so this is the idea of using microwave technology. And microwave technology is actually exactly what you have got in your mobile phones. So all one of you guys have some technology right now in your pocket which we critically use in our quantum computer at the University of Sussex. So, and what this allows is, I'm going to cut a very long story short, this different approach allows you to carry out quantum gates instead of aligning 2 laser beams, allows you to carry out quantum gates using the application of a voltage to a microchip. And so you can see already, like now we tremendously simplifying what it means to build a quantum computer, because you don't have to align all these laser beams anymore. You can now apply a voltage to a microchip. And let me take you through how that actually goes. So first of all, I'm going to show you here a scientific result, and I'm going to be in big trouble now because I'm going to define the y-axis of this graph as the quantumness. And all my honored Oxford colleagues here get me in big trouble after this because, so this is the quantumness. And basically, imagine if I have a curve like this, and if that curve goes all the way up, the quantumness is 100%. That means it's an unbelievably awesome quantum gate. And if that curve would just go like this, or just go randomly like this, then the quantumness would be non-existent. It would be like a conventional computer. So that tells you a little bit about how good that quantum gate actually works here. And so we have achieved, using this technique, a quantumness, or a kind of the smallness of the error, which is very close to this fault-tolerant threshold. And so that's very important when you talk about quantum computing, to think about where are you with respect to this fault-tolerant threshold. And so now I want to show you, I want to make you think about something when you build a quantum computer. And that is like, look at this thing of this quantum algorithm simulation being shown by, being simulated by Ike Chuang. So the more qubits you have, the more laser beams you'd need to make all these quantum gates. And so basically the number of qubits going to tell you how many pairs of laser beams you're going to need. So the number of pairs of laser beams is going to be proportional to the number of qubits. And so what is nice about this approach, which I'm going to show you, is that that actually goes away. And so this is going to be a long slide, so I'm going to prepare you here like, so, all right, so let me start this. So this is, I'm going to show you how we're going to do a different approach. First of all, now, atoms have these two trajectories, right? You know, that we have the two states, two trajectories. And we can also describe them as energy levels. You know, these two things here, these are energy levels, and they correspond to either having one trajectory or the other trajectory. And the energy to go from one to the other depends on the magnetic field you apply. And what actually depends, if I increase my magnetic field, that's what happens. That spacing increases. So the energy to go from one trajectory to another increases. If I decrease this, the energy to go from one trajectory to the other decreases. And so I've got this lattice of, you know, these X junctions here, and I can move my ions across this surface. And now as I change the magnetic field, so if I put the ion into a particular place by applying a certain voltage, I'm going to get a certain spacing of these states. And I have global microwave fields just irradiating my entire quantum computer, then because, and that's something you need to trust me on, or you need to believe me on, that's a bit of physics here, you trust me that atoms can only absorb radiation if the frequency of that radiation is exactly equal or to the spacing between these two lines here. And so basically, if the atom is in one particular place, nothing can be absorbed. If the atom now is in another place, there's a different magnetic field because there's a magnetic field gradient in this zone. So we can have different magnetic field where the ion sits. And if I just push the ion along in a different place, we'll feel a different magnetic field, and it will have a different spacing. And so basically by doing that, if I put it to a different place, the level spacing will change. And by changing the level spacing, it will now suddenly be able to absorb these global microwave fields. And if I put it again into a different place, then it will again absorb different microwave fields, and it will actually carry out a 2-qubit gate. So by this method, by just applying a voltage to a microchip, I can now achieve to execute a quantum gate with a set number of radiation fields. So I don't have to, as I increase the number of qubits, don't add more and more microwave sources or things like that. I literally just get the same number of fields. So this is, in a way, a bit of a comparison. So lasers are a very proven technology, so the best results have been achieved using lasers, but you have to be able to somehow align these lasers. You use mirrors and things like that. Now, microwaves are, in a way, a new technology, or relatively new technology, and one of the nice things is that you can electronically generate these things, and it basically becomes an electronic quantum computer. So that's, in a way, maybe a nice way to think of it. So you can actually take all the microwaves from external and just flood your whole quantum computer with radiation. You don't need to apply them on an individual place or focus them onto a region or things like that. So how do you go now about building a large-scale quantum computer? So first of all, you need these junctions. I already showed them to you, where you transport ions, you load them in, you move them across the surface, you bring them around the corner, and you can even bring them over there where you can detect the result of your computation. You do that by a laser beam which goes across a large part of your quantum computer, and then if the ion is in a particular state, it will fluoresce, and a detector inside this microchip can tell that, whether it lights up, and so you can then measure the result of the state. This is a microchip. I won't give you too many details about this chip, but it's a very sophisticated microchip which we've developed at Sussex in order to make this happen. And this is a picture of such a chip. So here you can see these square electrodes again, and so the ion again is trapped above the surface and can just move around and so on. And below this microchip is electronics, which generate all the voltages. So there's a lot of classical electronics, in fact, involved in making something like that happen. Right, but now let me ask you one thing. How do you actually make ion trap computers modular? Because different people will need different number of quantum bits. So you might need, for certain problems, you might only need 50 qubits. But somebody else here might want to do a problem where, Dominic, you might want to have 2,000 qubits or 2 billion qubits. So we need something modular so that people can use different sizes of quantum computers to solve their particular problems. And the biggest module will always be the size of a wafer you can fabricate, so you can never squeeze things into one module. So how do you make quantum computers modular? And one of the ways, and the most famous way to do this, is to connect each ion trapping module using optical interconnects. So we call them optical interconnects, and I'm going to explain what they are. So these are little modules like this. So these are the chips, and inside here now you connect them using optical fibers. And what you actually do here is you have to transfer the quantum state indirectly onto a photon, and then send the photon over to the other module. Or you can do something else. That's actually what's usually done. You entangle two ions, one ion here and one ion here, using photons which you combine together here. But again, this is really, you have to do some kind of a quantum physical process. It's not just sending light, but you have to really produce this entanglement. And that's very difficult. There's a lot of engineering. And this is what central mission of the NKIT Hub, to make technology to allow this to actually happen, to make such photonic interconnects, and that gives you a lot of flexibility. But at the same time, it's just unbelievably challenging the engineering in order to achieve such photonic interconnects. And David Lucas here sits here, his group is really doing amazing things in order to make this happen. So in my group at the University of Sussex, we pursued a different approach, what I would call a much easier approach, and that is to use electric fields to connect modules. So instead of using photons to transmit quantum information from one module to another module, we actually use electric fields. And so let me show you how that actually is possible. So this is the edge of one of these modules, and that's the edge of the next module. And when you now shape the electrodes on these edges in a right way, what you can achieve is that an atom which floats above the chip here can now move from this module, from the left module, to the right module by you just applying voltages. Now, obviously, there's disadvantages in that, because you can't build a quantum internet. You can't have a part of a quantum computer at home while you connect it to another quantum computer somewhere else. So this is really a way to build a quantum computer with large number of qubits, but with much less flexibility. The advantage is that it's a lot easier, because you don't need to transfer the quantum state onto a photon and send it over somewhere else. So this is the module we designed. So when you find your picture in the Daily Mail, it's usually cause for concern. That's happened to me like in a few months ago, because he probably had an affair with some royal or something, or did something even worse. So the reason why it happened in my case is because we published a blueprint to say it is now possible to build a large-scale quantum computer with tremendously difficult engineering, but you don't have to make any big physics breakthroughs in order to achieve that. And so this is what we published here. You can download this. This is a free, open access, so you don't need to have a subscription to look at this, at this paper here. And so you can see these are the microchips. There's the electronics on the bottom here. And using these electronics, which are below the microchip, you can now change all the voltages. And again, so this is one module, and now you can add all these modules together in order to make a quantum computer. Now to bring all of that together, I have a little film. So here, these are these X junctions. And you start now, you load your ions through a little hole into your ion trap. So you transport them over, and now you do the quantum gate. And you do the quantum gate using voltages applied to a microchip. So that's different here. You don't need laser beams for this. You still need some laser beams, but not for making quantum gates. So now you've used just these global fields and voltages, and changing the color here to signify change in voltage. Now you can transport the ions, and you put them, for example, across a detector which is integrated into the microchip. And you have a laser beam now which goes across the architecture. So you still need laser beams, but you can substantially reduce the number of laser beams. And now, if the ion is in one spin state, it will light up, and the detector measures that, and you know what ion the state is in. All of that goes on in parallel. So it's like really a big game of Pac-Man, and it just goes on here in parallel and all across this architecture. But eventually, your biggest size can be the size of any kind of wafer you can develop. And so this is what you see here. And now we have these piezoelectric transducers. They can move. They're things which can move, and they're attached to the bottom of these modules. And now now we can change the position of these modules in order to align them well enough that the electric field lines connect. And as the electric field lines connect, you can now see, so now the ions can't shuttle because the electric field lines don't connect properly. But as you now move these modules, you can see now I can connect them, and I can just transport the ions right across to the next module. And so this allows you now to create an arbitrary large-size quantum computer. Now, I've simplified quite a bit here, so you have to think about, this detection beam may expand a little bit, so you have to bring beams in and out, and obviously, this is an artist's impression, so, the vacuum system ain't gonna look just like that. But it's a way, the thing what we're excited about is it's a way to be truly modular. You tell me how many qubits you want, and we can do this. It's very, very expensive, it's very big, and so a few newspapers wrote stories when we published this and said, like, physicists propose football pitch-sized quantum computer, because eventually this thing could be huge. Could be depending on how many qubits you want. If you want billions of qubits, that literally would fill a building or maybe a football pitch. This is what we want to do anyway, because I think if you are able to build a quantum computer with such a large number of qubits, this would be very exciting. So funnily enough, like when we published this paper, like I had a journalist ask me about this, and I said, yeah, we'll do this at Sussex, and I realized I'd never checked this with my vice chancellor, so I went later to ask for the football pitch size space, which he happily agreed on. But anyway, so this is kind of an artist's impression of how this will look like. So let me bring things together. So what do we know? We know that it is possible to build a quantum computer with trapped ions. There's no fundamental physics barriers we need to overcome, no physics effects we need to overcome, and that makes trapped ions different to, I would say, nearly every other physical system. That's what is exciting about trapped ions. There's no fundamental physics we need to conquer. Is it easy? Absolutely not. Physicists tend to say it's just engineering, which is a horrible thing to say, because engineering sometimes can be unbelievably difficult, and here you have certainly a system where you have tremendously difficult engineering to achieve. What we're working on right now in NKIT is to build demonstrators. One at Sussex, where we use this technique I showed you, where we apply voltages to carry out quantum gates, and where we connect two modules using electric fields. At the same time, at Oxford, there's the 2020 engine being constructed, which is using laser beams and photonic links. And you can see how these things beautifully come together, combine different technologies, which are both extremely powerful in order to build very, very large-scale quantum computers. And in order to build large-scale quantum computers, which, say, can factorize large numbers, we still require 10 years. And that is not necessarily because of the physics breakthroughs we have to do, but the engineering is just very expensive. Right now, we're still kind of in a regime where we are academic groups and we have PhD students work on this, and we are now shifting to actually make this an engineering venture. So we're looking at making a spin-out company. We are starting to employ now more engineers than we employ physicists, because you can see all these challenges are really engineering challenges. So this is what we need to do. But so after this talk, obviously, there will be time for questions, but let me end this talk by asking you a question. So what could an unbelievably fast computer operating unlike any other technology we now do? Thank you very much.